So now let's look at a poker hand called a straight. So straight is a little bit more complicated because we identify some straights as being a special or different kind of hand that's more important. It's called a straight flush. So straight is any hand with 5 cards of 5 different denominations, which can be put in an order, like 2, 3, 4, 5, 6. All right. Except we don't want to count those if all the cards have the same suit, because those are called a straight flush, which is a better hand. So again, notice how many ways could we see a set of denominations that could be arranged in an order like that. Well, we could have 1 through 5, 2 through 6, 3 through 7, all the way up through 9 through 13. So that's 9 different ways that could happen. So this is a case where it's easier to actually overcount. So if we include straights and straight flushes and count those, all we have to do is first count which of these 9 sets of denominations we're going to have in our straight, and then for each of the 5 cards we can choose one of 4 of the suits. In other words, really what we have here is 9 choose 1 times 4 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 choose 1, or 9,216. But to get straights, we have to take that number and subtract off the straight flushes, because we don't want to count those. So straight flushes is just 9 times 4, because again we have to choose which of these kinds of straights we're going to have, and then we have to choose one of the 4 suits for all of them to be from that same suit. Another way to think of it is we choose the kind of straight, and then we choose one of 4 of the first card. Once we choose that card, its suit determines what our choice is for the rest, so we don't have any more choices to make. So we just take the total 9,216 minus the 36 straight flushes to get 9,180 straights. So that number is bigger than full houses. So a full house is better than a straight because it's less likely to get. So you also get flush, a hand that has 5 cards of the same suit. Again, it's a hand with 5 cards of the same suit, but we don't want to count straight flushes because those are a different kind of hand. So again, we look at flushes union straight flushes because that's somehow easier to count. Because if we allow all of those to count, we have to choose one of 4 suits to have in our hand, and then we just have to choose 5 cards from that suit. There's 13 cards, so 13 choose 5. So that's 5,148. But again, we don't want to count the straight flushes, we just want to count the flushes. So we have to subtract the 36 straight flushes from that to get the 5,112 hands that are called a flush. So again, this number is bigger than the number of full houses, so it's not as good. So a full house beats a flush, but a flush beats a straight because there's over 9,000 straights. So we can look at all the basic poker hands and count them all. So straight flush is best. You choose the suit, and then you choose which straight you're going to have. The 9, that's 36. 4 of a kind, it means you have 4 of one denomination and 1 of another. So again, we could choose the 2 denominations that we're going to create our hand from. For each of those choices, we choose one of those 2 denominations to be the 4 of a kind. We choose all 4 of those, and then we choose one of the other denomination out of the 4 to get 624. Full houses we've done. Flushes and straights we've done. We had to subtract off some things because it was easier to count the larger set and then subtract off something else. In a sense, what we're saying is to get a flush, we can't just use the multiplication principle. So what we did is we expanded that to a larger set, which we could apply the multiplication principle to, and then we use partitioning. In other words, break that up into 2 pieces and subtract off the stuff we didn't want. Same thing was done with straights. Now 3 of a kind is 3 of one denomination, and then 2 other cards which are not of the same denomination. So what that means is our hand has to have 3 denominations in it. We choose one of those denominations to be the 3 of a kind, and then we choose 3 of those cards, and then we choose one of each of the other 2 denominations. So 4 choose 1 twice. So 4 choose 1 times 4 choose 1. 2 pairs is if you have 2 of one denomination, 2 of another denomination, and then 1 card of a third denomination. So again, we choose 3 denominations, and then once we've chosen those 3, we choose 2 of them to be the pairs, or we could choose one of them to be the non-pair. 3 choose 2 and 3 choose 1 would give us the same number. And in general, n choose k and n choose n minus k are the same number. Because every time you choose, say, 5 objects out of 10, or I'm sorry, 5 objects out of, say, 20, you've actually chosen 15 out of 20 to not choose. So those are always the same value. But anyways, back to 2 pairs. We choose our 3 denominations. We choose 2 of them to be the pairs. For each of those, we choose 2 of the 4 cards, 2 of the 4 different suits. And then for the last card, we choose just one of those. And that gives us 123,552 hands that are called 2 pairs. Now pairs has a pair of one denomination and then a single card of 3 different denominations. So it's the same pattern here. 4 denominations are chosen. For each of those choices, we choose one of those 4 denominations to be the pair, and then we choose 2 of the suits of that denomination, and then for each of the 3 remaining denominations, we choose 1 card to get over 1 million hands called a pair. Now, a high card hand is basically every other kind of hand, where you have no pairs, you have no straights, flushes, or anything. You have kind of 5 cards that don't really do anything, so your hand is determined by its highest card. So what the idea is, it's a hand that has 5 different denominations in it. We count, we choose any of the 4 suits of each of those 5 cards, but we have to get rid of straight flushes because we could have picked a straight flush there. We get rid of flushes because we could have picked a flush by doing that. And we get rid of straights because we could have picked a straight doing that. We can do this because each of these 3 sets are mutually exclusive. Straight flushes, flushes, and straights are all mutually exclusive, but they all fall into the category which we actually counted, which was high card union those 3 things. It was just easier to count this with the multiplication principle and then subtract off the better hands that we could have gotten. And again, we get 1.3 million or so. And again, just dividing these by the total number of hands gives you the probabilities of each of these. I've given you that here.